All right, everyone, we're going to get started. This is going to be a lesson on chapter 8.6, concentrations, or rather, I would like to say solubility versus concentration, okay, or molar concentration, okay, or molarity, or even this symbol, square brackets. I'll talk more about this in a second. I hope you did due diligence for the previous lesson. It wasn't very mathy. It was a lot more just concepty on what a solution is, how water sort of plays out in creating a solution, what it means to be a concentrated solution, why a body of water has a certain limit to how much ionic compounds it can actually dissolve, so on and so forth. Please try the harder limiting reagent questions that I assign just to refresh, as well as the Google form that I have created in the form of quiz. After you go through this video as a lesson, study really hard, do the practice questions for chapter 8.1 all the way to 8.6. The quiz that I assigned, if you do well in it, it's going to be sort of an optional, sort of, I guess, extra bonus. The reason why I made this optional is because, number one, TDSC policy says, you know, you've locked in your grade and you can only go up from here. Number two, we're basically at the end of chapter 8. We're very, very close, rather. And I don't want to do a kind of huge Google form test on you with the problems that have everything there. Forcing, you know, this huge evaluation with like 50 marks on it, okay? Or like 100 marks, whatever. So do your best, all right? Molar concentration, the idea of molarity. First, let's talk a little bit about solubility. Up until now, I'm going to take a step back and do a kind of a math calculation question for solubility. Again, I said today we're going to be a little bit more mathy. Solubility, if you remember, is essentially the mass of the solute, in grams divided by what? Mass of water, but not just any mass, but specifically 100 grams of water, right? And of course, you know that if you use density, you can also say this is 100 milliliters. Anyways, that's not important. I'm going to erase that. Okay. So that's what it is. The concentration is going to be slightly different. So before we jump to this new topic here, let's really tuck solubilities underneath our belt. Here is a sample question that you can try. I'm going to type it up. What is, let's make it something applicable, something that you can actually visualize because you have some experience with it. What is the solubility of, how about hot chocolate, cocoa powder, if 22.2 grams of powder saturates a cup of water at room temperature? Notice how the wording is very specific. What do I mean by that? It's asking for the solubility of cocoa powder. Right? The only way you can actually calculate solubility is if we're actually talking about the maximum amount of cocoa powder dissolved. In other words, when I ask for solubility, let me highlight that, you can automatically assume that I am asking for a saturated solution. What is solution? What is the maximum amount per 100 grams of water if I dissolve 22.2 grams of it at room temperature? Note that solubility always comes with a temperature, so you can assume room temperature being 25 degrees. And a cup of water, that seems really vague, but if you know your stuff, then you can automatically assume that's going to be 250 milliliters. That is 1 cup of water, at least according to North American standards, I think. Let's move on, okay? So what is a solubility? What is the grams per 100 milliliters? Well, I think you can put it down. Solubility, right, is going to be, well, the mass in grams of the solute divided by 100 milliliters of, or 100 grams of H2O, right? This is what I'm looking for. Right now, what we have is 22.2 grams of the solute in 250 grams of water, right? Do you see how it's 250 milliliters, just automatically 250 grams? We have essentially, mathematically speaking, let's figure out what x is. I am going to do my little shortcut by cross multiplying. If you're not quite sure what the heck that is or why I'm doing that as an algebraic shortcut or why that's a shortcut in the first place, well, you got fractions, got to get rid of a division of 100, so I'm multiplying both sides by 100. Division of 250, multiply both sides by 250. You get 250x equals 22,200. No, 2220. Okay, that means x is equal to 2220 divided by 2500, and that gives you something on the calculator that I'm gonna have to open first. Okay, 8.88. Therefore, the solubility of cocoa powder is 8.88 grams per 100 grams of H2O. And that is correct because we're assuming a cup of water is perfectly 250, so it's a constant. It is not sig figs. 100 grams is perfectly 100 grams. It is not sig figs. So we have 3 sig figs given. We have 3 sig figs that we are going to report. Okay, that's it for solubility. So how is that different to concentration? Well, let me try to demonstrate. Concentration doesn't have particular, it's very similar in the equation, so concentration. But as you might have noticed, when we start talking about chemicals, we are not that interested in the actual mass per se because every single chemical has a different molar mass. It's easier for us to talk about concentration if we discuss an amount of solute in moles, of course, amount of solute divided by amount of, you got a 50-50 chance, solution. Some of you might have thought solvent. It's a good guess. Yeah, I want you to notice that it's actually not solution. So it actually is it states solution and not the amount of water. Some textbooks like to sort of interchange that. Why? They assume that you're using enough water so that even if you have something inside it and create a solution, the volume isn't that much different. But technically speaking, let's be true to the actual definition. Concentration is the amount of solute divided by the total amount of the solution that you have. And you'll see this being played out in the questions that I ask you. So molar concentration, so concentration being molar concentration is equal to, so again, molar, right? So the number of moles of the solute and divided by the volume of solution. Because you might imagine, a solution, we don't have the number of moles of a solution. A solution isn't pure. There's so many things in it. So you can only talk about it as a volume. And if I were to go further and turn this into an equation, capital C for concentration, molar concentration, molarity, whatever, is equal to the number of moles divided by the volume. Okay? So let's do it. Capital C is concentration. Little n, you know what this is. This is the number of moles. And V is going to be volume of solution. So units, obviously, for moles is just mole. And for volume, we always use liters. And therefore, if moles is being divided by liters, what is the unit for molar concentration? It's moles per liter. Always. Okay? Moles per liter is so common in chemistry that we have sort of names being thrown around for it. If a question talks about molarity, we're talking about moles per liter. If we talk, just as we were doing here, molar concentration, we're talking about moles per liter. If a textbook or a question just says, what's the concentration? Typically, they're using moles per liter. It's the most common. Even if I use square brackets, that's something you might have seen in grade 10 when you talk about acids, like pH is equal to negative log, H square, negative log of the square bracket of H. These square brackets right here is a shorthand symbol for what is the molar concentration of the hydrogen ions in the solution. Okay, you will see this often a lot more commonly in grade 12 or more like in university. I just want to give that there so that you're a little bit more familiar. Enough of this. Let's see how we can use this new formula, very important, new formula in basic concentration questions. Okay, here's a question. Example. Let's see, 63.5 grams of solid sodium phosphate, Na3PO4, is dissolved to make 500 milliliters of solution. See that? I'm not mixing with 500 milliliters of water. I am making 500 milliliters of solution. The wording is a little bit different than before. Okay, what is the concentration of the solution? So again, I'm already starting to use these terms, like throwing around these terms very simply, like you understand it, right? It's not solvent. I'm using 500 milliliters of solution, and I'm asking for what the concentration is. Automatically, you need to assume that I'm asking for moles per liter. So let's do it. What is the number of moles of Na3PO4? I don't know, but I do have the mass divided by the molar mass, and I could find that out. Just give me a second while I write out the other things. What is the volume that I want to make? I want to make 500 milliliters. But do not be fooled, please. Moles per liter is the unit. So I'm going to quickly convert that into liters, and they're asking for a concentration. This is what's happening. Give me a moment while I calculate the molar mass of sodium phosphate. That will be 3 times 22.99, 4 times 16, and 1 times 30.97. So that is 3 times 22.99 plus 4 times 16 plus 30.97. 163.94. 163.94. 63.5 divided by that is, so sig figs, 0.387. Concentration is going to be calculated by N over V. Again, this should be so smooth. C equals N over V. C equals N over V. C equals N over V. This is your bread and butter, people. Okay, so concentration is going to be 0.387 divided by 0.500 equals 0.774 moles per liter. And that's the answer. I'm going to add one more shortcut. Do you see how moles per liter, all this time, there's so many different names for it. And it's so common. We as chemists write this so often in our calculations, in our labs, in our whatnots, that we have a shorter way of writing moles per liter. You know, we talk about molarity. We can actually write this as 0.774 capital M. Now you might be thinking, whoa, 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 didn't we use capital M for molar mass? Yes, we did. Capital M, if we use it as a symbol of a number, of a quantity, that would be molar mass, okay? But if we have 0.774, if we use a capital M as a unit symbol, it's moles per liter. Some of you are like, oh, why? I get it. This is why I actually wanted to use molar mass as a different symbol. I wanted to use double capital M, but the textbook didn't do that, so I just like, whatever. Okay, either way, capital M is a universal unit for moles per liter. Capital M, if used as part of a formula like that, it's molar mass. If you want to change your equation and do capital MM from now on, you can, so that you don't get confused. But I don't think that's going to be a big deal. Okay, if you don't like what I just said, just use moles per liter from now on. Questions? Please email me. As a way to sort of, I guess, give you some harder questions, I'm going to do 2 more. For everyone else who feels that they have a general hang of this, I am going to ask you to stop the video because you've seen enough. Try the practice questions in the top right corner. Okay? Yeah. I have learned a new thing where I can actually clear everything that I wrote here. So if you haven't copied anything down, or you haven't finished copying down, do so by pausing the video. Otherwise, in 3, 2, 1, let's try another question. Another question is, let's see. Let's try number 2 from my works. Let's see. A saturated solution of aluminum fluoride, AlF3, aqueous of course, has a concentration of 1.536 moles per liter. If a 150 milliliter sample of the solution is removed and the water is evaporated, what mass of solute will be left in the evaporating dish? A bit of a mouthful. Okay, let's get to it. Once again, I notice that it has to do with concentration, so in the back of my mind, I have this already prepared, okay? This solution already has a concentration of 1.536 moles, okay? If I have a 150 milliliter, or I'm gonna quickly convert it, 0.150 liter sample of the solution, that's why I can put it here, is removed and the water is evaporated, well, how much of the mass would remain? So this is where your understanding of solution comes in. Remember, all of the moles are inside water. If the water is gone, then all these dots are what's left. Sorry, I should have done that instead. Okay, if all the water is evaporated, then all that's left inside the beaker is the moles. So using this, essentially what I'm asking is how many dots are actually inside it, how many moles are in there. Let's get to it. C is equal to N over V. If I multiply both sides by V, that means I have N equals C times V. Concentration 1.536 moles, volume 0.150 liters. That gives me 1.536.150, 0.2304 moles. In case you were wondering, 1.536 moles per liter is being multiplied by 0.150 liters over nothing. The units cancel out, leaving you with nothing but moles. That's why our answer is just moles. That's the end of this question. Shall we try one more before you get to go? Well, it's not like you can answer back, so I'm going to say yes, 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 we do. Last question. What volume of 0.850 capital M aqueous solution contains 45.3 grams of copper 2 nitrate, which is CuNO3 2, of course, aqueous. Okay, here we go. Let's break it down. What volume is what I need? It contains the mass of CuNO3 2 is 45.3 grams. And without even saying it, they actually gave me the concentration in a semi-sneaky way. So here's a solution that is of that concentration. If I use 45.3 grams, let's say in a lab experiment, what volume of the solution would I have on me? Okay, let's do it. Do you notice how this question subtly gives you the mass? There is no direct equation that connects concentration, volume, and mass, but from your previous practices, you should know that if you have mass, you automatically know the number of moles, and that is what you're going to need for this equation. So I really hope that it becomes very automatic to you, that this is not even something you have to think about. You're like, mass? Pfft, got it. Let's do it. The mass of copper nitrate is going to be 45.3. The molar mass of CuNO3 is going to be, perfect timing to close my periodic table. If you have it next to you, you might want to take your textbook out and go through the motions with me, because you're going to end up doing it anyways. If you're wondering where it is in your textbook, it's page 656. The molar mass of copper, 63.55, plus 2 times nitrogen, which is 14.01, plus 6 times oxygen, which is 16. Add that all together. 63.55 plus 2 times 1.01 plus 6.6, 185, 7.57. Let me redo that. 187.57 grams per mole. That means the number of moles is 45.3 grams divided by 187.57 grams per mole, which is 0.241509.8, so on and so forth. The question gave us 3 sig figs, 3 sig figs. I'm going to provide also 3 sig figs. Now that we have the number of moles, what is the volume? Well, please remember, if I multiply both sides by V, I get N equals CV. And if I divide both sides by C, volume is equal to N over C. So volume is equal to the number of moles divided by my concentration. And again, maybe I should go through the number of moles divided by moles per liter. And that gives us 0.2847285 liters. If I took this solution, and I know that I use 45.3 grams of copper nitrate, then I must have only had just over a cup of water of the solution available, 0.285 liters. Okay. Some of you who are sort of, keeping pace and you're always on the lookout for how this might link to topics in the future, seeing as how I'm using volume and concentration to calculate the number of moles, okay, you might realize that if I gave you an equation and I got you to do one of those charts for stoichiometry, hey, there is still a way that solutions can connect with the mass and the molar mass, just like you saw here. Pay particular attention to the questions like this and do your best. Before you try the solutions quiz, please try the textbook questions that I've already assigned. Ask me questions, do whatever you need to, and at the very last bit, when you know you've gotten enough practice, do the quiz at the peak of your I guess, awareness, your attention, your energy, whatnot. The reason I say that is because, as I said before, this quiz, I can make it worth marks to sort of help your current progress in this course. Hope this video helps. Ask me questions as I always do. And again, hopefully see you soon. Hope you're healthy and good luck.